Exactly. Hey Chris, it's good. How are you? Yeah, it's midterm season. I know.
Yeah, I've been really busy with labs and assignments and the midterm coming up for Wang.
Yeah, yeah, I know. It's a struggle. It's a struggle. It's a struggling time just because, I know a lot of you guys are close to graduating, and so I know you guys want to move on, but this is probably the time when you get the most work as a student because you have to juggle senior design. You're taking, all these really tough electives and you're finishing up your coursework. So it's tough. It's a tough time. Oh, dang. Oh, that's the lab, right? That's the heat transfer fluid mechanics lab. Oh, energy lab. I see. I see. Dang. I do not. I haven't taught any of the lab courses, um, but I've been thinking about it in the future. But I've been teaching I've been teaching a lot of the technical electives, and so that takes a lot of my prep time because these courses are pretty hard. So it takes me a while to prep these. So, but maybe in the future I might teach that class. Yeah, for sure. Okay. Oh, if you guys were talking, I apologize. The audio is muted. Now it's unmuted, so you guys can talk now.
Sounds good. How's the weekend? I guess I'm still muted, huh?
Yeah, I guess you're still muted.
Oh, still muted?
Mic check, 1, 2.
I try now.
Mic check, 1, 2.
Okay, there you go.
Hey, there we go.
There's a volume button and there's a mute button, so I had to undo both.
Oh, that's funny.
It's weird.
I was just saying, how was the weekend?
Oh, it was good. Yeah, I was telling Dr. Wang before this. I went with my wife to downtown Pasadena over the weekend. So it was nice. Just because in the past our schedules have always been really constrained because we had to feed our cat at certain times because she's diabetic, and so we had to be home for breakfast, we had to be home for lunch, dinner. But now all that is done, so we could spend kind of the day. So we're kind of exploring what life is like after post being a cat caretaker. No, we didn't go to JPL. I think my wife would be pretty bored at JPL actually, and so we just went to the downtown area. We ate something and we just walked around and looked at the stores and stuff.
And that's nice.
Mhm. It is nice, yeah. My friend described it as very Lululemon and Pottery Barn, and so if you know those stores, then that sums it up pretty well. Yeah, it's nice. It's definitely very nice over there. It is very expensive. That is right. Yeah.
No, what is it? A is the length. L. Yeah. Oh, wait, what, oh, A is the class. Oh, okay, so, right, yeah, so this, so C is the. Oh, actually, it's moving kind of section. Oh, okay, well, that's the distance.
The midterm is not open notes, and so you can have one sheet. You can have just one sheet of notes for you to work with. So you can have a 8.5 by 11 sheet. You can put anything you want, both sides, and you cannot use iPads, and so it's all going to be just paper, pencil. Okay, it's 5:30, so let's go ahead and get started today. All right, good afternoon, everyone. How's everyone doing today? Holding up, midterm season, so I know the semester is really getting busy for all of you. So, just hang in there. It's a tough time. Yeah, I know it's I can feel it. Even through the computer screen, I can feel the stressful energy from you guys. So, I know it's not an easy time, but I appreciate you guys being here. As always, I know you guys have a choice whether you attend class or not, especially because it's recorded, but I appreciate you guys being here because it's definitely a lot nicer to talk to people, even virtually, rather than it is just to talk to a webcam, which I've done before. Okay, and so the plan for today is we're going to finish up our lecture notes on 2D on convection. Okay, so after today is going to be the cutoff, and so after today, we're going to finish up convection and we're going to start something new on Wednesday. But today is the last lecture that you have to be concerned about with regards to the midterm. Okay, so remember the midterm is going to be next Wednesday. It's going to take place in class, and it's going to cover up to convection. And so I wanted to hold off on releasing the study guide until we finish the lecture today, because then you'll kind of have everything in context. Right? And so probably early tomorrow morning, I'm going to release the study guide for the midterm, which you can use to help guide your study. And I'm going to release a poll for you to vote on the topics that you want me to cover for the review video on Friday. Okay. I've also posted one more homework, just because the homework 2 didn't cover any convection, and so this homework 3 is to cover convection, and so that's going to be due next Monday. Okay, and so the homework will be due Monday. I'll put out the homework solutions on Monday night so that you can have them to study for the midterm on Wednesday. All right, and so I think that's all my announcements. So are there any questions I can answer before we get started? Okay, all right, so let's go ahead and get started. Okay, and so last time on Wednesday we were talking about solving convection problems using finite differences. And so we did all the 1D cases. And so we talked about this idea of, convection. Right? Okay. And so first we talked about what convection was. So remember, convection was the transport of some kind of material through a moving fluid. And the key here is moving fluid, right? And so the fluid that we have, or that can be transporting things, has a certain velocity. Okay. And what's most important about this aspect of the velocity is that it has some kind of direction, right? And so fluid, if you have a fluid flowing, there's a direction that it's flowing to, right? And so, we brought up the example of a fan, right? And so let's say we have a fan here that's rotating around. Okay. And as the fan rotates, it's going to push a wind or an airstream in a certain direction, right? And so anything that gets caught up in that airstream, whether it be, particles, we talked about like an air freshener, you can also have heat, or even the lack of heat, right? And so you can have blowing cool air. Anytime you have a transport of something with a moving fluid, that counts as convection, okay? And that directionality played a role in how we discretized our equations, right? Because one thing that, one concept that we introduced with convection was this notion of stability, right? Because when you have convection in a system, you have the possibility of your solution becoming unstable, right? And remember, we talked about instability as, when the solution does these kind of wild oscillations, right? But if we leverage the direction of the velocity, then we can change how we do our finite differencing scheme to make sure that we had a stable solution. Okay, and so in other words, what we did was we used the direction to define a stable upwinding finite difference scheme. And the idea with upwinding is that we would place more weight, either on the left or the right, depending on which side was the upstream direction, right? And so if we had a positive velocity like this, that's going from left to right, we'd place more weight on the upstream side. Okay. Which in this case, for a positive velocity, that would be a backward difference, right? So backward difference would place more emphasis or more weight on the left. And so that'll give us a more stable solution, okay? The alternative, if we didn't want to deal with, forward backward difference, because that's confusing, is that we can use a central difference scheme, okay? If we use a central difference scheme, we have to ensure that our grid spacing is small enough to get a stable solution, okay? And remember, the way that we assessed, or way that we checked to see if the grid spacing was small enough, was we computed what was called the Pequoi number. And so the Pequoi number, PE, was equal to the velocity U multiplied by the grid spacing divided by the diffusion coefficient, okay? And in order for our solution to be stable, then this Pequoi number has to be less than 2, okay? And so the key quantity here is the grid spacing. Where again, U is your velocity and K is your diffusion coefficient. And so if you wanted to use central difference, which again, there's a lot of good reasons for why you would want to do that, because central differencing has a much higher accuracy. You need to make sure that your grid spacing is, it satisfies this criteria. Otherwise, you might get an unstable solution. Okay. And so if you're going to use a central difference scheme, you would take the convection velocity, you would divide it by the diffusion coefficient. And then you would have to find the grid spacing that you would need in order to make sure the Pequoi number is less than 2. All right, so all that was kind of review from last Wednesday. Okay? And so now today we're going to take these ideas from 1D convection and then extend them to 2D convection. All right, so that was just a recap of our lecture from last Wednesday. So are there any questions on this? Okay. All right, so let's go ahead and get started with that. All right. Okay. And so convection in 2D domains, is not that big of a jump. And so, we just have a more complicated equation, but we're gonna follow the same steps that we've done before. And so we're gonna take our equation and then discretize it using finite differences. The biggest difference in 2D here is that, our velocity is not just going to be positive or negative. Our velocity now has separate X and Y components. Okay? Okay. Right, and so here, U is the X component of velocity, okay? And V here is the Y component. Okay. And so that's something to keep in mind. And so with that in mind, let's go ahead and write out our convection diffusion equation. Okay. And so our convection diffusion equation in 2D is the following. Okay. All right, so we have K times partial squared phi, partial X squared, plus partial squared phi, partial Y squared. All of those are diffusion terms. Okay. Then on the right hand of the equal side, we have U times partial phi partial X plus V times partial phi partial Y. These are our convection terms, because you can see that we have the convection velocities in front of these. Okay. And of course, we have Q, where Q here is our source term. All right. Right, so it's a bit more complicated than before, because now instead of just one convection term, we have 2 of them to deal with. Okay, and that means we have 2 decisions that we need to make in terms of how we're going to discretize this convection term. Okay. Okay. All right, so for now, we're just going to keep things simple. And so I'm going to apply finite differences to discretize this equation, but I'm going to use central difference for everything. Okay. All right, and so that means we're going to take all the derivatives here and then plug in their finite difference representation. Okay. By the way, and so you know, and you'll see problems like this on the homework, and you'll see problems like this on the exam too, where you know when I ask you to derive the algebraic equations that govern this system, I want you to do exactly this. And so I want you to start from the full differential equation like this, and then actually plug in their finite difference representations, and then work through the algebra to kind of simplify the terms. Okay. And so, you know, what I'm about to do now is, you know, what I'm going to expect for you for the, you know, on the homeworks and on the exams. Okay. Okay, so let's start with the diffusion terms. And so for diffusion, we have a k, okay, and then we have a second order derivative with respect to x. And so we plug in our second order finite difference equation here. And so that's phi I plus 1 comma j minus 2 phi I comma j plus phi I minus 1 comma j, all divided by delta x squared. Okay. Next, we have the y derivative. And so for the y derivative, we have phi I comma j plus 1 minus 2 phi I comma j plus phi I comma j minus 1. Okay, so all those are the diffusion terms. Next, we have the velocity terms. Okay. And since we're assuming central difference, I'm just going to plug in the central difference term for this. Okay. And so central difference for a first order derivative is we take the I plus 1 term. Okay. We subtract the I minus 1 term. Okay. And we divide it by 2 times the grid spacing. I'm going to do the same thing for the y velocity. Okay. And then finally, we have the source term that we're evaluating at node I comma j. Okay. Okay. And so all I've done so far is I've taken our original equation and I plugged in the finite difference approximations for all the terms. Okay. All right, any questions on how we got here up to this point? Okay. All right, and so now that we have the equation like this, let's go ahead and simplify it a bit. Okay. And so the way we're going to simplify this is we're going to take all the phi terms and move it to one side of the equation. Okay. It's a q, it's a plus q sub I comma j. Yeah, so that's the source term, and we're just evaluating it at the I comma j node. Yeah. Okay. We're also going to assume equal grid spacing. And so we're going to assume that delta x is equal to delta y. And I'm going to set that equal to delta. And so we're going to assume that it's all the same. Okay. And we're going to do one more thing. We're going to take, we're going to multiply this entire equation by delta squared. Okay. Just so that we don't have to deal with any delta in the denominator. So it just makes it a little bit more clean. Okay. Okay, so let me go ahead and do that. And so if we do that, we end up with the k. Okay. Then we have all the diffusive neighbor terms. We have phi I plus 1, comma j, plus phi I minus 1, comma j, plus phi I, comma j plus 1, plus phi I, comma j minus 1. Okay. Then we have minus 4 phi I, comma j. Okay, that's because we have two contributions from that. Okay. Next, we have the diffusion terms, or excuse me, the convection terms, which I've moved from one side of the equal sign to the other. Okay, so that's why I have a minus here. So that's going to be u times delta divided by 2, okay, times phi I plus 1, comma j, minus phi I minus 1, comma j. Okay. And then we have another minus the y convection term. So we have v delta divided by 2 phi I, comma j plus 1 minus phi I, comma j minus 1. Okay. And all this is equal to q I, comma j, which is our source term evaluated at node I, comma j. And then we multiply by delta squared. Okay. All right, let's go ahead and box this guy. And so this is the finite difference equation for our 2D convection diffusion. Okay. Okay. Right, and so if we know the diffusion constant, and we know the convection velocities, and we know the grid spacing, we can go ahead and plug all of these in, and we can apply this to any equation. Okay. All right. Any questions on this? Okay. I don't have this in the notes, but I do want to mention it because the next thing in the notes is actually to jump into the Matlab code. But just to give you an idea of what I expect on the homework and on the exam, you know, what I would ask you, I would first, of course, ask you to do what we had just done, and so, you know, apply finite differences to a differential equation and get it in terms of this. Okay? But the next thing I would ask you to do is to take this equation right here and actually apply it to a certain grid. And so I believe this was problem 3B on the last homework. Okay. But 3B gave you kind of a weird domain, and so let me give you a kind of a more standard one. All right. Okay. And so when I say to apply your finite difference scheme to a grid, I want you to actually come up with the algebraic equation that's needed for that grid point. Okay. And so let's say that I ask you to apply this for node 14. Okay. And so for node 14, you're going to apply this equation above here, and then plug in the respective ID numbers for, you know, the right neighbor, the left neighbor, the top neighbor, the bottom neighbor, and then node 14 itself. Okay. So let's go ahead and do that for 14, just so that you can kind of see. Okay. I think the way the homework, the way the homework states it is that you have to find the equations for all of the nodes. Okay. And so if that were the case, you know, you would apply this to all the nodes. But just for the sake of brevity right now, I'm just going to apply to node 14. Okay. All right, so for node 14, we have our diffusion constant. Okay. And we're going to multiply that by phi I plus 1 comma j. And so that is the right neighbor. Okay. Right, so we have phi 15 right there. Plus, we're going to add phi I minus 1 comma j, and so that's going to be phi 13 because that's the left neighbor. Next, what do you have? We have phi at I comma j plus 1, and so that's the top neighbor, and so that's going to be phi 19. Okay. Then we have phi at I comma j minus 1, and so that's the bottom neighbor, and so that's phi 9. Okay. And we have 4 times phi I comma j, which is the node 14 itself. And so we have minus 4 phi 14. Okay. All right. But we're not done quite yet. And so we still have our convection terms. And so our convection terms is going to be a minus u delta divided by 2. And that's going to be multiplied by the right neighbor minus the left neighbor. Okay. And so this is phi 15 minus phi 13. Okay. And then we're going to do the same thing for the y velocity. So y velocity, since we're using central difference, is going to be j plus 1 minus j minus 1. And so that's going to be the top neighbor minus the bottom one. Okay. And so this is going to be phi 19 minus phi 9. Okay. All right, so let's assume that the source term is 0. And so all this is just going to be equal to 0 here. Okay. All right, at this point, you know, usually it's good practice to group all the like terms. And so all the terms that have the same phi ID number, let's go ahead and group them together. Okay. And so first here we have phi 15. And so in front of phi 15, we have a k that comes from the first term. And we have a minus u delta divided by 2. Okay. Right, next we have the left neighbor term, so that's phi 13. And so that's going to be k plus u delta divided by 2, phi 13. Okay. Next, we have the coefficient in front of the top neighbor term, and so that's k minus v delta divided by 2. Okay. Okay. Then we have the contribution from the bottom neighbor, and so the bottom neighbor is k plus v delta divided by 2. Okay. Right, and then finally we have our contribution to our central node, which is node 14, and that only has a minus 4k. Okay. All right. And so when I ask you to, to solve for or compute the algebraic equation for a certain node, when I give you a grid like this, this is what I had in mind. And so this is the kind of equation that you should have in your homework and stuff. Okay. All right. Any questions on this? Okay. All right. Oh, actually, one more thing before we jump into the Matlab code. And so let's talk about stability. Okay. Right. So if you remember from our 1D case, if we're using central differences, then we have to compute the Pequoi number, where the Pequoi number is the product of the velocity and the grid spacing divided by the diffusion coefficient. Okay. But in 2D, we have two velocities, right? And so we have a velocity in the x direction, and we have a velocity in the y direction. And so the question is, which velocity should we use for the Pequoi number? Okay. And so for 2D, one way that you can do it is you can compute a Pequoi number in the x direction, okay, as well as a Pequoi number in the y direction. Okay. And so the x direction, of course, you're going to have the x velocity u. Okay. You're going to multiply by the grid spacing in the x direction, delta x divided by k. And then in the y direction, we would have v times delta y divided by k. Okay. And so this is the most general case. And so I know most of the time we assume that the grid spacing is the same in the x and y direction. But here, we keep it flexible for both. Okay. So that's why I have delta. So that's why delta x, delta y makes a comeback. And so in order to have a stable solution, both of these terms here have to be less than 2. Okay. All right. Any questions on this before we do an example with codes? All right. And so let me go ahead and define the example problem for us. All right. And so for this problem, let's assume that we have the following equation. Okay. What are my velocities? 30. And we have no source term. And so we're going to assume the source term is 0. Okay. All right, we're going to solve this on the following domain. And so we have a square domain here. Okay, and so we're going to assume we have all Dirichlet boundary conditions. Okay, we have 25 on the south side and the east side, and on the west we have 50, and on the north we have 50. Okay. All right. And so normally, when you're given a problem like this, and and I saw this a lot in the homeworks, where for the homeworks, I think a lot of people just jump straight to the code. And most people just submitted code for their last homework. But I still want you guys to run through some of the setup on paper, right? So because there's still some setup that you should do on paper, and I think if you do that, it makes implementing the code a little bit easier. Okay. right? And so your first step should always be to take the differential equation and then actually, apply finite differences to get the finite difference equation, okay? And so I know it might seem like a waste of time because, you're going to be writing the code for it anyway, but you'd be surprised that, if you write it out on paper first, it keeps a lot of your work organized, and it ensures that you're kind of, you have the coefficients in the right places, okay? Because as I was grading the homework, and I talked to quite a few of you last week, kind of just with help on the homework, a lot of the mistakes that I found was that people were either putting coefficients in the wrong place, or they just couldn't visualize what the matrix looked like, right? And so if you write out the equations on paper first, that'll show you, what one row in the matrix would look like, right? And what each equation would look like. And so when you go to implement it in code, you can use that knowledge to help you debug, right? And you'd be surprised how much it helps you to debug, because if you kind of already know what equation you should be looking for, and what the matrix should look like, and that'll help solve a lot of your issues with the coding. Okay. So I'm not going to do it again here because we've already done it up here, and so you would just follow the same process that we followed up here, right? And so you would take your differential equation, plug in the finite difference approximations, and then kind of massage it algebraically in order to get a simplified expression like this. Okay. But just because I want to make sure that we finish the code today so you can do the homework, I am going to jump into the Matlab code. So any questions before we jump? We make that jump. Okay, all right. So let me go ahead and share my screen here. Okay. So can everyone see my Matlab screen? Okay,
Yeah.
so this code is, let me go ahead and bring it out to the side. Okay. All right, so this code is posted on Canvas. And so if you go to the Canvas site, and let me close this, and you go to our page for week 6. And so here's the home page. And you click on the link for week 6. And there should be a code at the bottom of this page called 2D Convection Diffusion Finite Difference Starter. Okay. And so the starter code has a lot of blanks that we're going to fill in throughout the class today. Okay, so that's the starter code. But if you don't get a chance to finish it in class, or you're still working on home, the solution is here as well. And so if you go to code right here, I believe it should be this one. This one. Yeah. So it should be 2D advection diffusion finite difference, or this one right below it. Right? And so the solution for it is the same name of the file, but just without the starter code there. Okay, so let's look at this. Let's look at the code here. And so I've broken this up into several different sections. Okay. Is the font size okay? Can everyone read the font size? Okay. Okay, great. Okay, so let's start in section 1. And so in section 1, we are defining the variables. Okay, so these define all the problem parameters of our problem. Okay, and so we're going to assume that the length of each side of the domain is just 1. Okay, so we have Lx, Ly is equal to 1, and we're going to assume that we have 50 grid points in each direction. Okay, and so let me coarsen this up a little bit, because 50 by 50 is going to take a little bit time to run, and so let's change this to 25. So it'll be a 25 by 25 first. Okay. And so now that we have the number of grid points in the X and Y direction, we can compute the total number of grid points. And so that's just going to be the product between the two. And we can also compute the grid spacing, right? So the grid spacing is going to be Lx divided by nx minus 1. And the grid spacing in the Y direction is going to be Ly divided by ny minus 1. Okay. All right. And so next we have the left-hand side matrix, which we are defining to be zeros at first. Okay, and so we have LHS matrix is equal to zeros of n total comma n total. Okay? And then we have the right-hand side vector, which is where our boundary conditions and where our forcing function is going to go. And that's going to be a zeros vector from n total comma 1. Okay. All right, and so the next part is probably the most important. And so we're going to define our diffusion coefficient as well as our X and Y velocities. And so our diffusion coefficient here is 3. Okay. From the problem. Our X velocity here is 30, and our Y velocity here is 75. And so in this first section of the code right here, all I've done was I basically defined all the important parameters that we're going to need for the rest of the code. Okay, and so that includes the geometric parameters in terms of the length, the number of nodes that we have, as well as the physical parameters of the problem in terms of the diffusion coefficient and the x and y velocities. And so remember, I structure all my codes very similarly to this, and so I like to have kind of this top section right here dedicated to just defining the variables, so that we don't have to worry about it later on. Any questions on any of this? Okay. All right. So next thing we're going to do is we're going to define the interior nodes. Okay. So we're going to use our finite difference equation to define what the coefficients are for this. Okay. And so this section is called populate the left-hand side matrix for all the interior nodes. Okay. And so you can see here I have our patented nested for loop. And so we have a for loop that goes from I is equal to 2 to nx minus 1, and then a j that goes from 2 to ny minus 1. Okay. And remember, we do this because we can only apply this for the interior nodes, right? So the interior nodes need to have a neighbor on all sides, and so we can't do this for the boundary nodes. And so that's why we do our loop here from 2 to nx minus 1, and then 2 to ny minus 1. Okay. Okay, and so now here we're going to start inputting some code, right? And so you can see here I've left a lot of the code blank. We're not really blank. I told you where you need to put in code. Okay. And so the first thing we need to do is we need to compute ID numbers for all of the adjacent nodes. Okay. And so we have my ID, which is the central node in the stencil. We have the node for the left neighbor. We have the ID number for the right neighbor. We have the one for the upper neighbor, as well as the neighbor below it. Okay. And so remember our equation for just if we have the nodal coordinates I and j, which is what we have here in the loop, the way that we compute the ID number is we take nx, we multiply by j minus 1, and then we add I to it, right? And so that's the convention that we're using in this class for the nodal ID numbers. Okay, and so we've done this before in the diffusion code, and so but I want you guys to kind of get practice with it. I want you to take this equation here and then modify it for the left ID, the right ID, the up ID, and the down ID. Okay. And so what you can do is you can take this equation and kind of copy and paste it here for all the entries here. Okay. But you're going to make a modification for each of these, according to which neighbor it is. Okay. So remember, the left ID here is phi at I minus 1, comma j. Okay. The right ID here is phi at I plus 1, comma j. Okay. Our upper neighbor here is phi at I, comma j plus 1. And then our bottom neighbor here is phi at I, comma j minus 1. Okay. And so once you guys go ahead and spend the next couple minutes and modify these 4 lines of code right here, so that they compute the appropriate ID numbers for the neighbors. Okay, and so I've given you the phi indexes here, and so you have to make just very small modifications to these lines of code to ensure that they compute the right ID numbers. Okay. All right, so I'll give you guys just a couple minutes to do that before we move on. All right, so let me go ahead and fill these in just so I can catch up. Okay, so for the left ID, remember we have I minus 1, and so we're going to replace I here with I minus 1. Okay. For the right ID here, we're going to replace I with I plus 1. Okay. For the upper neighbor, we're going to replace J with J plus 1. Okay. And then for the bottom neighbor here, we're going to replace J with J minus 1. Okay. Of course, you can simplify this, and so we have a plus 1 minus 1, and so that's going to cancel out. You can take out these parentheses as well. Okay. And then J minus 1 will be minus 2. Okay. But again, that's how we compute the ID numbers for each of those nodes. So if you remember the example that we did earlier, where I gave you the grid points and I said to find out the equations for node 14. Right, and we just looked at the grid to see which were the upper and lower neighbors. This would give you the exactly correct ID numbers for those nodes. Okay. All right, any questions on how we did these ID numbers here? Okay. All right, so next we have to start making contributions to the left-hand side matrix. Okay, and so let me go ahead and bring up the nodes. And so remember, the coefficients are these terms that are in front of the fees, right? Because the fee terms are in our solution vector, right? So remember, the system that we're working with is we have a matrix like this, okay, and here we have all the fee terms. Okay. Right, and so the entries that we put in the left-hand side matrix have to do with whatever coefficients are in front there, okay? And so I kind of broke this up, and so you don't have to do it like I did, and so I broke it up to kind of match what we have here in the notes. Okay, so that we can kind of introduce the diffusion terms on one side, on one kind of block of code, and then we can introduce the convection terms on a different block of code. Okay. Okay, so let's do the diffusion coefficients first. Okay, so for the diffusion coefficients, let me bring back to the notes. Okay. You can see here that we have a positive k multiplied by the left neighbor, a positive k multiplied by the right neighbor, by the bottom neighbor, by the top neighbor, and we have a -4 times k for the central node. Okay. So let's go ahead and apply that here. And so for the left ID, okay, so this is the coefficient for phi. I minus 1 comma j, okay, for diffusion. And that's because we have, we're in the my ID row and the left ID column, right? And so the coefficient for this was a positive k, okay, where our k here is given by the variable diffusion. Okay, and so I'm going to say that this coefficient here is going to be equal to diffusion. Okay. Okay, and we have this exact same coefficients for all the other entries, right? So for the right neighbor, we have phi I plus 1 comma j. Okay, so I'm just doing diffusion right now, so we haven't touched convection yet. Okay, so if we're considering diffusion, all the neighboring terms have just a positive k in front of them. Okay, and so that's why I have just a diffusion here, because diffusion here represents our k variable. Okay. But for the central node, and so this is just straight up phi I comma j, right? Right. So what's the coefficient in front of the central node, right? And so for the central node here, you can see here we have a -4 times diffusion, right? Because this diffusion is gonna multiply through. And so the coefficient that we have here is going to be a -4 times K, which is diffusion. All right. Any questions on how we did that, or why we set those coefficients the way that we did? Okay.
Yeah, quick question. So just
yeah.
to reiterate, the diffusion basically covers everything already for us.
So the diffusion covers just this block right here.
Yeah, just that entire block.
Exactly. Yeah. And so diffusion here is just equal to 3. And so if you look back up earlier in the code, diffusion here is a simple variable which is just 3. But in our problem here, our diffusion coefficient K is equal to 3. And so from our equations here, we can see that we have a coefficient of, if we distribute this through, we have a coefficient of 3 here, a coefficient of 3 here, 3, 3, and we have a -4 times 3, and so there's going to be a -12, right? And so we've taken care of the contribution from this part of the equation by using that diffusion variable. Okay.
Okay.
So the reason, but the reason I didn't put just 3, 3, 3, 3, and 12 is that I want this code to be flexible. And so if I were to say that, I changed my mind, let's do a problem where the diffusion coefficient is 8. Okay. And so since I did everything in terms of this diffusion constant, then when I put 8 right here, it's going to automatically update everything else in the code, right? And so, just like I've kind of been telling people in office hours and stuff, it's best if you set up your codes to be kind of flexible like this. Because it's true that you can set this equal to like 3, you can set this to 3, you can set this to 3, 3, and you can make this to -12, right? And so that would be correct. And so that would be correct for this particular problem. But if you wanted to change your code, if you wanted to change it to a different diffusion coefficient, which is very common in computational work, then you'd have to go in here and change all of these things. And so, it's better to kind of leave these in terms of, let me just undo all this stuff. It's better if you kind of leave these in terms of kind of generic variable names and then define the variables up here, so that if you want to make a change, then you just have to change it in one place versus having to change it in like, 5 or 6 or a dozen different places. Okay, and so now that's all the diffusion contributions. And so now let's add the contributions to the convection terms. Okay, so let's start with the X convection. And from this equation here, you can see we have a contribution to the right neighbor. Okay, and we have a contribution from the left neighbor. Right? Okay. And so we're going to need to make two assignments. Okay. And you can see here that the value that we're going to input here is a u, which is the x velocity multiplied by the grid spacing divided by 2. Okay. And so let me just input this in code first. Okay. And so we have a u times the grid spacing. Okay. And we divide that by 2. Okay. And then for the right ID, if we go back to the notes here, the right ID has a minus sign out front, and the left ID has a positive sign out front because this minus sign is going to distribute through. Okay. And so for the right ID here, we have a minus u. U here is the x velocity, and so you can see here that the x velocity that I've defined in this code is called xvel. Okay. And so we have xvel. Okay. We're going to multiply it by the grid spacing. And so the grid spacing we've computed up here as well. And so the grid spacing here is dx. Okay. Okay. And then we're going to divide by 2. Okay. And then for the left ID here, we're going to have the opposite sign. So we have xvel times dx divided by 2. Okay, so one's positive and one's negative, and that's kind of what the central difference does. Okay. Okay, and so we've input the convection coefficients in for those terms. Okay. But would this work right now? You know, think of what we've done with the diffusion contributions, and think of what we're doing now with the central difference, right? Notice that here that I'm making a contribution to my ID, right ID, but we've already done that up here, right? And so, you know, if we run this code, like, do you think it would work the way that we want, or do you think we'd have to add a little bit something to make sure that we don't overwrite something that we've done before?
Would we have to write a hold on or something like that?
Not a hold on, but we would have to use our update notation, right? Because, you know, we've already gone through the trouble of assigning this diffusion coefficient here. And so we don't want to forget it. And so we want to make sure that we keep that value there. And so one way that we can do this is that we can change this line here. Instead of just setting this equal to this value here, we can say that, you know, we can take what was there before, right? And so we could say that left-hand side matrix at my ID comma right ID is equal to left-hand side matrix at my ID comma right ID minus xvel times dx divided by 2. Okay. And remember, you know, when we use this notation here, this instructs MATLAB to use the old value of what was there before, which in this case, what was there before, which was just the diffusion, and then just add to it. Okay. And so in this case, we're just going to subtract. We're just going to take the diffusion and then subtract xvel times dx divided by 2. Okay. And we're going to do the same thing for this one right here. Okay. And so remember, you know, when we use this update notation here, that means we can retain what was there before, but then just add to it. Okay. All right. Any questions on why we did that? All right, so let's go ahead and do the same for the y velocity contributions. And so for the y velocity contributions, we're going to have for the upper ID, that's going to be a minus y vel times dy divided by 2. Okay, and we have a positive y vel times dy divided by 2. Okay, but just like we saw up there, you know, we don't just want to assign it here because we already have stuff there. And so we don't want to delete what's there before. And so let's change this to update notation. Okay. And so we take what was there before and we just add or subtract from. Okay. Okay. Question. So is that method different than using the diffusion term? Yeah, it's a bit different. So the diffusion term, you know, we didn't worry about it because we know that before we started assigning stuff here. And so at this point in the code, the row in the matrix is empty. Okay? Where empty means that all the entries are 0 for this row. And so you know, we're building this matrix kind of row by row, right? And so we're only going to be looking at one row at a time. And so, you know, since we're never going to visit a row more than once, you know, whenever we kind of come back to the top of this loop, we can be assured that our row is all zeros at that point. And so we can just do a simple assignment here, and we don't have to worry about you know, we don't have to worry about messing anything. And so that's why for the diffusion term here, I just did a simple assignment. But, you know, once we got to the convective contributions, then I want to make sure we didn't override the diffusion. If you want to be really, really sure, you can make the update notation for every single line of these codes as well. I believe someone asked me about that, I think last time as well, or maybe 2 classes ago. And so you can do that. You know, but here it's not necessary because at this point, every entry in that row is 0, you know, before we start assigning stuff. All right, any other questions on this part of the code here? Okay.
Sorry, you said that the row in the matrix is empty. And then what was that part in the parentheses?
Oh, all the.
Oh, okay. Oh, yeah, I see. All right, thank you.
Yeah, yeah, because we're starting with the matrix that's completely zeros. Okay, and so that's all of the interior nodes. Okay, so the next thing is we have to apply the boundary conditions. And so in the interest of time, I'm just going to go ahead and speed this up. Okay. And so first we're going to apply the essential boundary condition on the left-hand side. And so for the left-hand side, we have, remember when you're applying boundary conditions, you only have one loop because we're only visiting nodes on one side. Okay. So here we have nx multiplied by j minus 1. And the special condition on the left boundary is that all of the I values are 1, right? Because normally we have this. This is our generic ID number equation. But since we're on the left boundary, I'm just going to plug in 1 for y, or excuse me, for I. Okay. And for a Dirichlet boundary condition or an essential boundary condition, remember we put a 1 on the diagonal. Okay. And then on the right-hand side, we put the Dirichlet value. And so the Dirichlet value for this is 50. Right, because that's what the problem stated. So if you go to the example problem right here, okay. So this is the domain that we're solving on. And so since the Dirichlet value on the left-hand side of the domain is 50, then that's why I assigned a 50 on the right-hand side there. Okay. Okay, so now we have the top boundary. And so the top boundary, we have the special condition where j is equal to ny, right? And so we have nx multiplied by ny minus 1, okay, plus I. Okay. We're going to put a 1 on the diagonal entry. And then the RHS vector value, and so this is the Dirichlet condition. This is going to be 50. Okay. Where did the 1 came from? You mean on the diagonal here? Yeah, so the 1 came from because you know, when we assign the Dirichlet boundary condition, we basically make the equation phi at I comma j is equals to 50. Right? So that's the equation that we're putting into the matrix. And so the 1 comes from the fact that this coefficient in front of the phi right here is 1. And so this LHS matrix MyID says that we're going to be setting the coefficient for this term right here for phi I comma j, and the 1 tells us that, you know, we're putting the coefficient in front of this guy right here. Okay, so I'm going to do that for the right boundary now. And so the right boundary has the special condition where I is equal to nx, and so we have nx multiplied by j minus 1 plus nx. Okay, we're going to put a 1 on the diagonal. And then since the Dirichlet boundary condition there is 25, then I'm going to put a 25 there. Okay. And next, we have nx, or the bottom boundary where j is equal to 1. And so we have a 1 minus 1 plus I. Okay. And of course, you have 1 minus 1, so this guy's going to go away. And so you can just have I there. Okay, but I'll just leave it for now. We have a 1 for the diagonal, and then a 25 for the Dirichlet value. Okay. Okay. And so so are there any questions on how we apply these boundary conditions? So these aren't any different than before. So these are kind of the same as what we did for you know, for our 2D diffusion cases. All right, and so now that we've implemented all these things, I've already written all the rest of the code to solve the system for you and to display it. So let's go ahead and run the code. Right, and so here, zoom. Okay. And so here you can see our solution, right? Right, and so here you can see what's happening is that basically we have our normal kind of distribution here, but it's kind of smushed because of the convection velocities. Okay. And so I believe we had a convection velocity of 30 and 75. Okay, and so we have a more dominant velocity in the y direction. Okay, and so that's why you see that this plot is really smushed up here, right? Because that y velocity is kind of pushing up the curve so that you have a very small, very small strip right here. Okay, and in fact, I can make this even more fine. Okay, so let me make this 50 by 50. Okay, so you can get a little better resolution here. Okay, and you can see the plot a little bit better from here. Okay. Okay. All right, and so there's our solution. Okay. All right. So was anyone able to get this solution by following along in the class today? Okay. Good. All right, and so now that we have the code like this, let's experiment with it a little bit, okay? Because remember what we talked about before, and I didn't mean to do that. Okay. Remember before what I said was that we, in order for this code to be stable, our Peccary numbers here have to be less than 2. Okay. So let me compute the Peccary number in the x direction. Okay. So remember the Peccary number in the x direction, the way we compute it is we take the x velocity, okay, we multiply it by the grid spacing in the x. Okay, so that's going to be dx. And we divide it by the diffusion. And so you can see here that our Peccary number in the x direction is 0.2, and so this is very stable. Let me compute the Peccary number in the y direction. And so the Peccary number of the y direction will be the y velocity multiplied by the grid spacing in the y direction. Okay, divided by diffusion. And you can see here the Peccary number in the y direction is 0.5102. Okay. And so in other words, both are stable. Okay. So that's good, and that's what we see. That's what we see in our solution too, right? Oh, I closed it, and so our solution was stable. Okay. And so let's change that, and so let's see what happens when we make it unstable. And so I'm going to take the y velocity, just the y velocity, and I'm going to change it to 1,000. Okay. And so we've increased our y velocity here by a factor of 15 about. Okay. And so let me go ahead and run the code again. It's a little bit harder to see because it's not as obvious as the 1D case, but you can see if you look at the graph right here, and let me make it a little bit bigger. Okay. Bigger. Okay. You can see here that we have some kind of oscillations in the solution. Why the hell is this green? Make it red. Okay. Right. And so you can see here that our solution jumps from like a high value, which is yellow, to a dark blue value, which is a low value. Then it kind of jumps up and down right here. Okay. And so this kind of jumping around here, even though it's not the same as our 1D case, we can see the colors kind of fluctuate wildly. This is an example of an instability. Okay. Right. And so, that instability is a result of our Peccary number being too high, right? And so if I go back to the console here, okay, let me recompute the Peccary number in the y direction. Okay, so remember our Peccary number is our y velocity multiplied by dy divided by diffusion. Okay, you can see here that our Peccary number in the y direction is 6.8, which is much greater than 2. And so now we have an unstable solution. Question. So I said that the yellow to black to green to blue represents instability. Yes. And so there's very few cases there's very few physical cases where you're going to have a rapid oscillation of the solution right here. So you can see that the solution is jumping up and down. And so if you look at the color legend here, you can see that the yellow represents a value of 50, and the darkest blue here represents something that's like, maybe about 10 or something, right? And so you jump from 50 all the way down to 10. And so that's both the maximum and the minimum of the graph, existing in very close proximity. And so that's that's an instability. And so whenever you have such a huge kind of big jump like that from the maximum to the minimum, then that's an instability. And the fact that it kind of rubber bands, it kind of oscillates back and forth, that kind of shows that this solution is unstable. Okay. And so to make this stable, what we can do is we can reduce dy. Okay. And so if we take dy, okay, knowing that the Peclet number has to be 2. And so if we change this code in order to make dy equal to that, 0.006, then we can make this solution stable. And so, so our old grid spacing was 0.2. And so probably we would have to reduce this by a factor of, let's compute that real quick. Okay, and so we'd have to have 170 grid points in each direction in order to make this stable. Okay, so don't try this. And so if you try it, it'll probably make your computer it'll probably run, but it'll probably take you probably about an hour to run this. So don't do it. Okay. And so that would be a case where you would probably want to use an upwinding scheme. And so instead of using a central difference here for the y, maybe you change this to like a forward difference or a backward difference in order to make it stable, right? Because if we had a situation where our velocity actually was 1,000, then this 50 by 50 grid is not enough, and so you'd have to refine it even more in order to get a stable solution. Okay. Okay. So does that make sense? So does it? Are there any questions on this instability here? Okay. All right. So let me do one final thing before we go. So let me change the x velocity to 1,000 as well. Okay. And so now we have a ton of velocity in the x direction, a ton of velocity in the y direction. So we have really, really fast, right? And so we've already seen that when we change the y velocity to 1,000, I believe what it was before was we had 30 and 75, right? Yeah, 30 and 75. Okay. We've already seen that when we change this y velocity to 1,000, we made our solution unstable, right? And so what do you think is going to happen when we change the x velocity to 1,000 as well? Let me move this here. Right? Do you guys think it's going to be unstable? It should be very unstable, right? Because it's going to be unstable both in the x and the y direction, right? And so let's see. So let's go ahead and run the code and let's see what happens. And so you can see here we have a little bit of instability here. And so if you look at kind of the top right of the graph, we have a little bit of instability here. We have a little bit of oscillations, but it's overall it's not bad. And so we actually get a solution that looks fine. And so we have kind of a smooth transition here from the yellow to the blue. And most importantly here, we don't have any kind of spurious oscillations. And so the minimum here is 25, which is exactly what we set to be our boundary condition. Okay. And so we have kind of a paradoxical case here. So we have a case where, which should be really unstable because we have a, really high x velocity and a really high y velocity, and we didn't make any changes to our grid. Okay. And so you would think that this solution here should be, extremely unstable. But when you have convection phenomena in 2D, you have kind of an additional phenomenon that can happen, and that's called cross-stream diffusion. And so we're just about out of time, and so I don't have time to really explain it today. But basically, the idea with cross-stream diffusion is that since our grid here is aligned in kind of like a very kind of, tic-tac-toe X, connect forward type of grid, right? And so we have kind of a very uniform grid right here, okay? What can happen sometimes is that if your velocity vector is not aligned with the grid, okay? And what I mean by that, is that it goes some direction like this. So let me use a different color. And so that's essentially what we have here, is that we have a velocity that goes kind of at a 45-degree angle to our grid, right? Because both the x component and the y component are the same, right? And so it's basically a vector that points up and to the right at a 45-degree angle, okay? And so when the velocity is not aligned with the grid like this, then what can happen is that you can have some artificial diffusion that gets added to your system, okay? And that artificial diffusion is called cross-stream diffusion, okay? And so what the cross-stream diffusion does is that it takes your normal k here, okay? So in this case, we had k is equal to, what was it? Our k is equal to 3, I believe, right? Yeah, k is equal to 3, okay? When you have cross-stream diffusion, it augments this k to make it even greater, okay? Right, and the degree that which it increases your diffusion depends on how much how unaligned the velocity is from the grid, okay? And so we've actually looked at the worst case where it's about a 45-degree angle. Right? And so when we come back on Wednesday, I'll go ahead and give you the formula for cross-stream diffusion, as well as talk about what you could do to mitigate it, because it's usually you usually don't want it in your solution. Okay, and then after that, and then we'll finally close up our unit on diffusion, and then we'll start talking about unsteady problems. Okay, so are there any final questions before we wrap it up for today? Okay, all right. So that's all the time we have for today, and so thank you guys for tuning in. I know it's a busy time, so I appreciate you guys coming out to the lecture and keeping me company. And so I hope you guys enjoy your evening. Get started on the next homework. I know it's a little bit short of a lead time, but it's important stuff that's going to be on the exam. So make sure you get started with that. And if you have any questions, just go ahead and let me know as usual. Okay. So thank you guys. I'll see you on Wednesday.
Hey, Professor, have a good one.
Thanks, you too.
Thanks again, Professor. Take it easy.
Thanks, Chris. You too. Carol, did you have any final questions? Okay, all right. So I got to go run to another class. Okay, so you've got, okay, bye.